Greetings everyone, my name is Lalwat Felarantli. I am a curator at the Sri Krishna Science Center, Patna. So as a continuation to our popular lecture series, today we'll be talking about quantum computers. This talk will be a non-technical treatment, so it's as the title suggests, it's really a brief introduction to quantum computers. So when we talk about computers, we usually think about this and this. So we play games, we watch movies, we write documents, we prepare documents, and then also the internet connectivity. So whenever we talk about computers, we think about this. But what makes them run? What is inside them? So that we'll be talking about in this in the coming slides. So first of all, we will start with a brief historical review of computations or computers in general. First of all, we hear the word analog computers. By analog, literally, it means similar. Analog or analog, it means similar. But with the advent of digital electronics, analog electronic means the signal whose variation is continuous, which vary continuously. And in digital electronics, the signal vary discrete, in a discrete fashion. So that distinguishes analog electronics and digital electronics. So eventually our modern computers are based on digital electronics, and hence we call them as digital computers. So the first computation facility or computer of its kind is the first known is the Abacus, which is an acronym. It stands for Abundant Bits Addition and Calculation Utility System, and this is the picture. This is Salamis Abacus, Greek 300 BCE, before Common Era. The oldest abacus survived to the present day. Unproved information suggests similar to abacus device was used in Babylonia as early as 2400 BCE. So this is not the first abacus, but it is the oldest that exists, that survived till present day. And this is a modern replica of a Roman hand abacus from the 1st century CE, Common Era. Or CE, Common Era means AD. And this is a Chinese abacus. So these are used for counting, calculating, or more specifically computing. Now this is a Herman Planimeter devised by Johann Martin Herman in 1818. So this is a mechanical setup which does the kind of integration which we have known in calculus, in mathematics. So given a curve or given a shape, it can calculate or integrate the area. It can calculate the area or integrate the function. So this dates back as old as 1818, the year 1818. So next is the Thompson's disk globe cylinder integrator. So we have a disk here, and a globe, a sphere, and a cylinder. So the disk, the rotating disk causes a sphere. When the disk is rotated and the sphere moves in the y direction, this is just called as y. It can be called as x, y, anything, a, b, c, anything. And then this motion passed to the cylinder. If the disk rotates q dx amount, if the disk is rotated q dx amount, then the sphere will spin through a distance of qy dx as it moves, causing the cylinder to turn qy dx divided by r, where r is the radius of the cylinder, the number of cylinder rotations does correspond to the integral of y dx. So it's basically an integrator, a mechanical integrator. Integration, as we have known in modern calculus, it actually does that. So this comes in a scientific paper, Royal Society of London, in 1876. Now next comes the Babbage Engine, which was devised in 1834. He did not live long enough to build this engine, but he gave the idea. And he, Charles Babbage, he is regarded as the father of computer. This is his idea. I mean, the machine that he had foreseen. He designed the first analytical engine that overshoots the existing difference engines, which can perform only addition. So difference engines, which we have discussed before, are nothing but they perform only addition. So they are called difference engines. So, but this Babbage engine, or the analytical engine, or some people say, some people regard it as difference engine version 2. The analytical engine, it can perform four basic arithmetic functions, as well as works on the principle of modern day computers. The four basic arithmetic functions: addition, subtraction, multiplication, division. So in reality, multiplication is nothing but repeated addition, and division is nothing but repeated subtraction. But anyway, these are the four basic arithmetic functions. And apart from that, it works on the principle of modern day computers. It means input, central processing unit, memory, storage, and output. So these are the basic working principle of the modern day computers. So Babbage was the one who envisaged this principle. So the first, with the advent of digital electronics, transistors and all these things, the first electronic general purpose digital computer was made in as new as 1945. It is called ENIAC, Electronic Numerical Integrator and Computer. This is the picture at the Penn Engineering, University of Pennsylvania. So the second one is Electronic Discrete Variable Automatic Computer, EDVAC. It was devised in 1946. It's a binary serial computer. Binary means now it becomes binary means it is based on 2 units. So we'll discuss in the coming slides. With automatic addition, subtraction, multiplication, program division, and automatic checking with an ultrasonic serial memory capacity of 1034-bit words. At VAC's average addition time was 864 microseconds, and its average multiplication time was 2,900 microseconds, quite long enough. Now, those electronic computers are mainly based on transistors. These are the, I did a Google search with the keyword early transistors. So these are the early transistors, bulky enough, because of that we have bulky computers before. Now with the advent of digital electronics and integrated circuits, those transistors, thousands of transistors are embedded in just a single fingertip, which fit to a fingertip dimensionally. So these are the circuits integrated circuits on a chip. So the advancement of technology in the electronics, in the digital electronics, enhances the advancement of computers and computations as a whole. So after 1960, the advent of integrated circuits changed the whole technology. Now we have logic gates. So these logic gates, these are just symbols, but inside the logic gates, we have a number of transistors, these kind of transistors. So we'll talk about these things in details. So we have NOT gate, AND gate, NAND gate, OR gate, or NOR gate. So these are the basic. Especially the NAND and NOR gate are called the universal gates because any other gates can be derived from them. Here we also have exclusive OR gate, XOR gate, and we can make different kinds of gates based on our requirements. So these are the basic. And moreover, what I would like to highlight here at this point is input is either 0 or 1. That means on or off. So we'll talk about this. These 0 and 1s, they are called bits or binary digit, 0 and 1. So in digital electronics, we call them discrete electronics. So discrete values, these are called 0 and 1. They are used to specify the on state or off state. So a certain, let's say 0 does not mean no voltage. So let's say, for example, on a scale of 5 volts, a voltage less than 2 may be regarded as 0 state, and more than 2 may be 1 state. So something like that, we can tune our circuit to work like that. On state means more than 2 volts. I mean, just for an example. So off state means less than 2 volts. Whether it is, the circuit actually may be on, but the on state has to be more than 2 volts, and off state may be less than 2. So now a single bit can be 0 or 1. Now when we say 2 bits, we can have 4 combinations: 0 0, 0 1, 1 0, and 1 1. And 3 bits we have this, and then 4 bits, 5 bits, 6 bits. So 8 bits is what we call as byte. So example, we have this. And then kilobyte is thousands of bytes. Megabyte means million of bytes or thousands of kilobytes. And gigabyte means billion of bytes or hundreds of thousands of megabytes. So for any n bit, n can be 1, 2, 3. For any n bits, there are 2 to the n values. So let's say when we have 1 bit, there are two values. When we have 1 bit, there are 2 values, 0 and 1. When we have 2 bits, there are 4 values. That means when we have 2 bits, 1, 2, 3, 4, and so on. When we have 3 bits, 1, 2, 3, 4, 5, 6, 7, 8. So when we have 8 bits, more 256 and more. So each having n bit length. So n bit n can be 1, 2, 3, and so on. So working with these bits, we have our whole world, digital world. It runs through each and every part of our daily life, official, non-official, personal, business, everything is running digital now. Even the country is going for a digital India. We are going for a digital India. So what actually lies behind all these things will be, it's more of a technical that can be treated in some other technical session. Now we will enter through quantum computing. So the computation based on the bits 0 and 1 are called as classical bits, and the computers that are based on those computations which we have discussed before, 0 and 1s, are called classical computers. Now when we say quantum, we mean quantum mechanics. So the mechanics or the movements, the motions that happens at the atomic scale, they are small enough. At that scale, the classical mechanics or Newtonian mechanics cease to hold. They fail. So that is the reason why we have a new physics called quantum mechanics. So the computers that perform computation using quantum mechanics, the principles of quantum mechanics are called quantum computers, and those computations are called quantum computation. So the most important phenomena are the superposition and entanglement and many more. So now in quantum computing we have quantum bits, or called as qubits or quantum bits. So this straight line is called the these are angular bracket, and this straight line, this is just the notation in quantum mechanics. So these are called bracket, this is bra and ket notation. So it's nothing but notation only. So the one state is called like on in classical computation. On state is 1, off state is 0, and superposition means a superposition and addition or linear combination with certain coefficients A and B. This is called superposition. So in quantum mechanics or in quantum computation, apart from having a one state, on state or off state, we can have a combination of on and, which is partially on, partially off state. So A and B, in terms of probability, the on state can exist with a probability A, and the off state can exist with a probability B. But eventually when it operates, it will operate as the on state or off state. But the physical reality or the state can exist in this superposition. That is the beauty, or that is the speciality of quantum computation. So for n qubits, we can have a state in any superposition of 2 to the n basis states. For a 1 bit, we can have 2 basis states, a superposition of 2 basis states, and then it adds up like that. So, but in quantum computation, we can have additional this. That is the difference. It is a superposition of 2 to the n basis states. This is the difference. Now, this is just for an example. In classical computation, either 1 state or 0 state. So this can be regarded as the, let's say, the magnitude of the voltage. A certain value of voltage can be on state, can be on state. Below that will be off state. So in quantum mechanics, what we are doing is the information can be processed in a by harnessing the atomic level. So here the spin of the electron can be used to carry information. So let's say when we say entanglement, superposition we have talked about. Now let's say for an entanglement, for every electron we have upspin and downspin. So we can have this as we can call this as a downspin, and this can be called as an upspin. So if the spin states of the electron, spin up or spin down, are used to carry information. Let's say I create a code or a password or a secret code, a key for encrypting some information. Once I receive a downspin, I know that upspin is there. So in certain way they are entangled in the sense that they are related. So this is the kind of situation, the security or the reliability, or the security in terms of information processing, which a quantum computation can offer. So we'll see that in some other sessions. So using those quantum computation, we can have various quantum logic gates as such, and the matrix size of n qubits is 2 to the n cross 2 to the n. It's quite maybe a bit technical, so we'll go through this. So the difference between classical computing and quantum computing, I will just read them out. Classical computing, it is used by large scale multi-purpose computers and devices. Quantum computing is used by high-speed quantum mechanics based computers. Information is stored in bits. Information is stored in quantum bits or qubits. Discrete number of possible states 0 or 1. There are infinite 2 to the n basis states superposition. Continuous number of possible states. Calculations are deterministic, meaning repeating the same input results in the same output. However, in quantum computing, calculations are probabilistic, meaning there are multiple possible outputs to the same input. So it can exist in the superposition. So any one of them can always be the outcome because they exist in certain non-zero probability. Data processing is carried out by logic and in sequential order. However, in quantum computing, it is carried out by quantum logic at parallel instances. Thereby, it saves time. Classical computing operations are defined by Boolean algebra, zeros and ones that we are familiar. However, in quantum computing, they are defined by linear algebra over a Hilbert space. These are quite theoretical. So, classical computing, circuit behavior is defined by classical physics. However, in quantum computing, circuit behavior is defined by quantum mechanics. So, let us compare more about to break a widely used RSA 2048-bit encryption and encryption, which is of the size 2048. RSA means RSA is a public key encryption technology developed by RSA Data Security Incorporation. The acronym RSA stands for Ravesh, Shamir and Adelman, the inventors of the technique. So to break a RSA 2048-bit encryption, a classical computer with 1 trillion operations per second, 1,000 of billion is called trillion. So per second, trillion is a million of million, right? So per second, classical, this is also very fast, would need around 300 trillion years. A classical computer with this much speed would need this much years. No one will survive just to break this encryption. However, a quantum computer with only 1 million operations per second could achieve the same task, the same feat in just 10 seconds. This is the difference between a quantum computer and a classical computer. So casually we can say this is actually this is a impossible task. 300 trillion years. We will not live to see the result, but a quantum computer can do, with a slower speed, but in just 10 seconds. 1 trillion operations per second, but 1 million operations per second, but complete in 10 seconds, but this will complete in 300 trillion years. This is an estimation. So that is the difference between a quantum computer and a classical computer. And 20 years of quantum computing growth. So the first of its kind was built in 1998. Okay, by the way, when we heard about computers, as we have seen in the previous slide, we think about this PC, the desktop, the cabinet, keyboard, monitor and all. So at this level, whenever we talk about quantum computer, it's more of we talk about the processor. We are talking about the processor mainly. IBM, Oxford, Berkeley in 1998, 2 bits with a 2-bit quantum computer. In 2000, Technical University of Munich, 5 bits and then 7 bits, 12 and so on. 2019, 128 bits. And then this is a picture of a quantum computer. So the quantum computer, the circuit looks like this. This is that the plates look like this, a qubit, a coupler and all these things. The quantum computer is being cooled with liquid helium to achieve superconductivity. So it is maintained at very, very low temperature. So in 2019, Google claimed quantum supremacy with their computer, with their quantum computer called Sycamore, 53-qubit processor. It's a processor, okay? Because it reportedly performed a task in only 200 seconds. So it's less than 5 minutes. That would have apparently taken a classical supercomputer 10,000 years to complete. A classical supercomputer would take 10,000 years, but their 53-bit processor quantum computer can complete the same task in just 200 seconds. So that is the difference between a quantum computer and a classical computer. So now, as I have mentioned before, when we talk about quantum computers, we mean we are talking about the processor. Now it's the whole field as a whole is in the development stage. So the possible applications can be most important. The 10 most important application fields can be in cybersecurity. So this is going to be very, very important. Those entanglement, superposition, and all those things. And drug development, financial modeling, better batteries, efficiencies, cleaner fertilization, precision, because at the quantum level everything will be, maybe traffic optimization, weather forecasting and climate change, artificial intelligence, solar capture, electronic materials discovery, and all. I would like to add some note. It's nothing like it's nothing like a quantum computer will replace the classical computer as we have used in our daily life. But the thing is, a quantum computer can do certain job which a classical computer cannot do. So they work. The principle on which their computation is based is they are different. So they operate differently. It doesn't mean that internet downloading will be fast. It's not something directly as like that. But whatever a quantum computer can do, the number of ways it performs a certain job is relatively lesser. So, as it was mentioned before, it's in the development stage. It may be able to design, to work, to do in more areas of field. So, it's always better to be updated in the field and learn more about quantum computers. Thank you.